main speaker tonight is Greg Silsby. Greg is a professor at Horn Point. He's got his BA degree from Queen's University and another degree from the University of Waterloo. He speaks a little funny, you might notice. It's Canadian by background. But anyhow, he's going to teach us all how to fly and how to find clean water out there. Greg?
Yeah. Thank you. Thanks very much. I'm Greg Silsby. I'm a research professor at Horn Point Lab. It's not a BA. My background's actually an environmental engineer. Then I did this 4-year degree in environmental engineering, came out learning nothing about the environment. So I ended up doing my graduate work in biology, specifically in water quality. As I said, I'm Canadian, but I've done work all over the US and all over the world, really. My master's, I did a lot of work and lived actually 2 years in East Africa. There's lots of large lakes over there. Predominantly, they're managed for their fishery, so there's not much finance or effort being done to look at the water quality of the lakes. So I went along with these people doing surveys on fisheries and tried to teach these scientists some basic water quality measurements that they could do alongside their fisheries surveys. Then for my PhD, did water quality in the Laurentian Great Lakes, moved around a lot, Europe. I was in Oregon State for a while and University of Georgia. Finally, I landed here with my wife, who's also a professor at Horn Point Lab. So thanks a lot for having me. So one of the things I'm going to begin with my talk with, I'm not going to jump straight into the science of what I do, but I just wanted to talk about, I don't know how many people of you know or have met research professors. So I just wanted to explain basically what we do. And the reason why, I saw a statistic recently that public trust in science is now at something like 40%, whereas 10 years ago it was at 60%. So there's been an erosion for whatever reason, I'm not entirely sure, in the trust in science. So I'm one of these people that I'm happy to sit behind my computer and pump out research papers and happy doing that. But I think it's important, and really thank you for inviting me here to come and talk to you, because I think this is maybe one of these steps that I could do as a scientist to help increase confidence in science. All right, so first, how many people have heard of University of Maryland Center for Environmental Science? Almost everybody. How many of you knew that we're actually 5 institutes in total? A couple of you. Okay, yeah. So basically, University of Maryland Science, it's really all-encompassing. We've got research labs all the way up in Frostburg in the Appalachians, big lab down in Solomons, the Chesapeake Bay Lab. I'm at the Eastern Shore, at Horn Point Lab. And then we've got Institute of Marine Environmental Technology right next to Boston Aquarium. So really, it's a pretty big institute. We're now a degree granting institute. So, if you come and do your graduate work with us, you don't get a PhD from University of Maryland, you get it with us. And we're predominantly a graduate school. So at all these research labs, it's only graduate students and research professors. So our mandate is really mostly, it's a little bit of education, but a lot of research. We've got lots of core research. Research. I'm going to take this off so I can. That's a bit better.
Hey, Greg.
Yeah.
You lose my mic on that too. So.
Oh, I'm sorry.
Sorry. You can do the stand if you want to. How about that?
Yeah.
I need you to stand with me on that. I'm sorry.
No worries. All right, now I can see. Lots of different core research areas. Of course, today I'm going to be talking about Chesapeake Bay, so a lot of it's related to water quality. But we have, our researchers, they're out in the Indian Ocean right now. They're all over the world. I'm still doing research in the African Great Lakes. We're interested in fisheries and aquaculture, some of the more new molecular techniques, looking at genes and microbes. Biodiversity is a big one, as is restoration science. So this is public information, so I'm happy to share it with you. It's basically the finances of University of Maryland Center for Environmental Science. So that left graph, they call it expenditures. I think it's basically where our money comes from. And as you can see from this pie chart, a little under 50% is coming from the state of Maryland. And the big one I wanted to talk to you about are our contracts and grants. So basically, state of Maryland, they pay our salaries, they pay for the electricity of our buildings, but it's up to us as researchers to go to institutes like the NOAA and National Science Foundation, or in my case, often NASA, and we write research grants. And basically, just to give you a sense how this works, and the success rate of these research grants, it's about somewhere between 10 and 15%. So basically, I have to write 8 or 9 research grants. They'll go to a panel, it'll be peer reviewed, and they'll say, okay, fund these guys, fund these guys. So, you know, I probably wrote about 20 research grants this year. I think got 3 funded, so I'm pretty happy with that. Why I mention that is just, you know, it's a competitive environment, and it's making sure that the tax dollars that are going to these funding agencies are being put to really the top quality science as judged by, you know, the institutes themselves, be it NOAA or National Science Foundation, and our scientific peers. I should also say, please feel to interrupt me at any time and ask questions. I don't really, this could be interactive, it's probably better that way. I'm not a gifted speaker, so I always, when I'm lecturing to my students, I'm like, please interrupt me at any time. So just some of the research highlights. Has anyone heard of, probably most of you have heard of the Chesapeake Bay report cards? Anybody? Yeah. So these come out of University of Maryland Center for Environmental Science. They're done quite often, every year in fact. Chesapeake Bay, I think this is a 2016 one I'm showing up. Basically, what these scientists do who are responsible for these, they look at lots of different metrics. A lot of them are water quality metrics. Some are related to things like menhaden and fisheries in general. And then they basically pool all this data together and come out with a letter grade as you would get in public school. So right now we're at a C for Chesapeake Bay. I think a couple years ago it was a C minus. So there's a good trajectory towards improved water quality in the bay. But you can see up where we are, we're in around the D minus area. So some work to be done in this area of the Chesapeake Bay. But as you could tell from those core areas, we've got just really a huge gradient of research. We've got socioeconomics. I'm just putting up some of the 3 papers that were recently published from UMCs. One was in it's really prestigious magazine, or journal I should say, Nature, where one of my colleagues looked at managing nitrogen at the global scale for sustainable development. A student that I advise has done some work on impact of sea level rises on the tidal ranges in Chesapeake and Delaware Bay. And sort of in this paper, he projected out in the future with increasing sea level rise. What does this mean for inundation? I live in Cambridge, Maryland, which is pretty low-lying. Right now I'm renting, but I'm looking to buy a place. So I go and ask this PhD student, well, I found a really nice house near the water. What's it going to look like in 20 years? Like, how often will it get flooded? And then more in line with what I'm going to be talking about today, we have people that are expertise in harmful algal blooms. We've got a grant right in with the National Institute of Health where we're actually going to be we propose to fly drones to monitor harmful algal blooms in Chesapeake Bay. All right, so now I'm going to get a bit more into the science of my talk. So just for an outline, what I do is actually pretty easy, and you'll see, you don't need a PhD to do what I do. I'm dumbing it down a little bit, but it's not that complicated. I'm just basically going to talk about watercolor and how what's in the water shapes the color of the water and how you can use that information. We're going to talk a little bit about what that means for water quality in general, and then how we can measure this, be it with a satellite or drones. And then I'll just open it up for questions and discussions. I'm interested in what you guys are doing. And citizen science, it's becoming a really important thing. I got an email from a gentleman, I don't know if he's here, and they're flying drones around some of the tributaries in Chesapeake Bay and wondering what to do with that data. All right, so at the risk of being Captain Obvious, exactly, which water would you rather swim in? It's a rhetorical question. We've got a beautiful tropical beach, nice blue water, and then something entirely different, extremely brown, extremely turbid water. So it's pretty obvious how color really is driven by quality. The water quality is really a function of the color of water. So I was lecturing today, and I always ask my students questions, so I'll do it to you. So just shout it out. Name some things in the water that give it color.
Algae.
Algae, great one. Algae, sorry, what else? Mud. Sediment. Sediment is kind of mud. Yeah, so mud is like organic sediment. Someone said oxygen? Tannin. Oh, who said tannin? That's the hardest one to get. Yeah. Yeah, seagrasses as well. Yeah, so those are like basically the big four things. So basically what I'll try to do now is explain how the sort of science behind measuring those things.
Does that color go all the way from the surface to the bottom, or is it the surface?
So that was a picture I took in Africa, actually, and it was in a nearshore area, so a lot of that was just mud and sediment being smooshed up. And it was in a very shallow area. If we took a boat out maybe 800 meters, it was still like, you wouldn't want to swim in it, you definitely wouldn't want to drink it. But the water quality did improve a little bit as you went out further.
I scuba dive, and a lot of times that real green stuff is very shallow. So when you get that bright green, it's a product of the depth of the water in addition to the clarity.
Okay, so here, this is stuff you guys already answered your questions when I asked it out. So basically, I haven't included seagrasses here, but I should have. But in the top left is a picture of the upper Chesapeake Bay after Hurricane, I think it was Irene. And just all that rain brought in so much sediment into the bay that this is a picture from space, from a specific satellite. Normally, the water would be a lot darker, but all that sediment in the top left picture is making it appear a lot more brown. Top right is algae. I also will probably use the word phytoplankton. It's a little bit more scientific. It just means phyto being plant in Greek and plankton being free-floating. So these are the microscopic plants that are the base of the aquatic food web. So they're the things that eventually feed the menhaden. So there's a good amount of phytoplankton. You want a little bit, but not too much. We'll talk about this. And the gentleman who said tannin, good for you. Tannin is basically dissolved organic matter. So you get it around like wetlands a lot. I don't know how many of you have been down by Blackwater Refuge. It's a tidal wetland. A lot of organic matter comes out. It's broken down, dissolved. It basically colors the water brown. In fact, for visual aid, this is just distilled water. And there's your tannin, so really like a tea color. Looks a lot like tea. In fact, that's what tea is organic or dissolved organic matter. This is just regular old algae. I don't know if you could probably not see it, but I've got two different concentrations. So a little bit of algae, see pretty well clear through it, and then a ton of algae. It's extremely dark green. And some mud. So So we're going to talk about the differences in that color and how we can use satellites and drones to sort of infer, basically taking a picture and then seeing, okay, well, this is a lot of algae, a little bit of algae, some tannin, not so much tannin. Okay, so the science basically behind using drones, using satellites to infer water quality, the first thing you need to know is a little bit about the nature of light. So this is the electromagnetic spectrum. What we refer to as light is just really colloquially a small part of the electromagnetic spectrum. So on the left, we've got really high energy light that's like gamma rays or X-rays that you'd get in like a medical machine. Fortunately, the sun does put out some of that electromagnetic radiation, but it's all absorbed in our ozone layer, so it never hits us. UV radiation, I'm sure you've all heard of that. And then into the visible wavelengths, so basically think of a rainbow going from blue on one end to red on the other, and then into the infrared and radio. So today we're going to be, because we're talking about color and visual, our visual interpretation, we're going to basically stick to the visible spectrum. But I should just note that, I don't have it here because I don't have Wi-Fi. I was going to show you just like the amount of satellites that NASA and European Space Agency have right now in orbit staring down at the Earth is confounding. There's at least 30 satellites just through those two organizations. Koreans have satellites, Brazilians have satellites, and all these satellites have little specialized cameras on them that use some feature of this electromagnetic spectrum to do different things. So for one thing, like, in all these hurricanes and the hurricane tracking, I'm sure you've all seen these images on the news. They use basically infrared radiation to track like cloud movement and hurricane movement. There's just tons of applications. But for today, we'll just stick to color. Okay, before I get to my next slide. So this is pure water. Doesn't have much color. But if you could imagine you're out in the middle of the ocean, and the only thing in the ocean, there's nothing in the ocean except water itself. What color would that be? Sorry? Blue. Blue is correct. Do you know why the ocean is blue? Not quite. All right, you'll learn something today. Yeah, that's exactly what the next slide's going to show. Okay, and this is how basically the science behind what we do as remote sensors. So here's your visible spectrum. Everything absorbs energy, but it doesn't absorb all types of energy equally. So this is what we call an absorption spectrum on this graph. Where if the dots at the low energy mean it's not absorbing very much light at all, and as you increase, it's absorbing more water. So what you can see from this graph is that pure water itself, absorbs a lot of red light, a lot of yellow light, but does not absorb blue light at all. So that basically means because it's not being absorbed, eventually that light is going to be scattered back. And that's what you see. So for example, I've got a red shirt on. That means it's absorbing all those other types of light, but not red light. So it's sort of counterintuitive. But that's basically how you'll see why this is important coming up. So it's a good thing to keep in the back of your mind. Okay, a little more straightforward. This tannin or dissolved organic matter, sort of brownish, would you say? Yeah. So if you look at the absorption spectrum, it's the opposite. It's not blue or it's not purple because it's absorbing all that light. Instead, it's this brownish red color because none of that light is being absorbed. So it's what we see coming out. So pretty straightforward.
So, back up the slide.
Yep.
And what are you telling me right there?
With the graph?
Yeah, with dissolved organic matter, is that like really bad?
No, it is what it is. It's just dissolved organic matter. We'll get to the implications in a second. Dissolved organic matter is just dead leaves. Yeah, dead leaves, dead plants. It's like tea. Whether it's good or bad, this is a picture. I was up in the Pacific Northwest. This was just a stream coming out of the mountains. Super brown water. I can't say it's either good or bad. I mean, it doesn't really feed anything. It feeds bacteria. And not all bacteria are bad.
It's natural.
It's natural. Thank you. But I appreciate the clarification. So similar things. This time it's not. This time we're talking about phytoplankton, so the green bottle. So basically, going back to your grade 10 biology or whatever, I'm sure you guys have heard of chlorophyll molecules and how they harvest light and drive photosynthesis. This is basically what the absorption spectrum of chlorophyll and some other pigments look like. So they're really good at absorbing blue light. And they're really good at absorbing red light. So what's left over, what's not being absorbed is what we see, and that's basically the green light. And the other thing I haven't really shown in these slides, but that's why I brought these bottles along, is that the concentration of these things, be it organic matter, sediments, mud, or algae, the more there is, the greater contrast in color there is. So this is sort of an example of how we use this type of data. So this was some satellite data that passed over Chesapeake Bay. It's unfortunate I don't have that NASA app up and running, but basically, there's different satellites measuring different things. This MODIS satellite that I'm talking about, it passes over Chesapeake Bay every 2 days, and it scans the water and measures all these different wavelengths of light. So it can tell how blue it is, how green it is, how red it is. And basically what we can do with that information is to make some predictions on water quality, assuming that there aren't any clouds, of course. So the simplest algorithm in sort of this field of optics is estimating how much algae there are in the water. So what I've done in this image is I've taken the green wavelength and the blue wavelength, and I just did basic NASA. They have published algorithms on these. Basically, the more green it is, the more algae there are in the water. And that's it. And so from just these satellite data, you can get really good spatial maps, a spatial representation of how much algae there are on the water. So in this graph, the red is really high biomass. Purple would be really low. We don't see that in Chesapeake Bay. And sort of green on this scale is more moderate concentration. So I guess I should back up a bit and talk a bit about the utility of satellite data. It takes a lot of money to go out in a boat and do all these measurements yourself. For instance, if I were just I go out on Chesapeake Bay about every month, and I go out and take my water samples and do some other measurements, maybe fly my drone, and it costs me about $300 a day for fuel and for the rental of the boat. And I only have so much time, so I can only hit so many stations, so many specific areas. Whereas with satellite data, you can really get a huge spatial range, and the data is free. And it's like NASA, you always hear about NASA being like a flagship US governmental organization. They're just so organized, and they make it so simple that anyone in this audience, if you've got some sort of basic computer skills, you can go on the internet, do a quick Google search, and find something like, say, air temperature data, or in my case, phytoplankton biomass or algae, and get a record since whenever these satellites started. So this specific satellite has been measuring since 2002. It just died actually a couple weeks ago, but that's okay because NASA's got another satellite that started in 2014 and the Europeans have satellites. So there's just a huge wealth of data that's publicly available. But the other thing you'll notice just in this graph is, you know, where my thing is a bit broken, where we don't have data, like especially in a lot of the tributaries we don't have data, and in some areas we don't have data. Part of that is clouds, and part of that is the reason why I'm going to talk to you a bit about drones in a bit.
What's the yellow?
The yellow color, it would be like pretty high concentrations. So that is, I'd have to look at the scale again. I just meant this to be non-quantitative exactly, or just for the sake of this presentation.
It's a little bit less than red.
It's a little bit less than red, thank you. Yeah. It's pretty high, let's say that. It's around, if you're in the water quality, if you know your water quality data, it's around 10 micrograms per liter of chlorophyll, which to me is pretty high. The global ocean on average is 0.2 micrograms per liter. Something like a harmful algal bloom that you would really visibly see with the naked eye, like 10 micrograms per liter, you would definitely notice that in the water. So yellow, that yellow and up is, you're like, okay, that water is pretty green.
In a prior life, I had a brother who lived in Alaska. We went up there and visited, and they would have these really neat looking rivers. They would be gray, and he said, that's glacier. It affects rock and stuff, and he said, there's nothing alive in there. There's no fish. I mean, is that because the light is blocked out, or?
Yeah, so, I mean, this is my mud sediment, and it almost looks a bit gray.
Right.
So I talked about the spectral characteristics of algae. I didn't talk about sediment because it really depends on the type of sediment. So something like glacial till,
Like rock.
yeah, it basically, if you've got a river or a tributary with like really high sediment, even here, I guess the thing that's deleterious for the environment, it doesn't allow any light penetration. Yeah. So things like seagrasses are, you know, just can't grow there because they need light.
Thank you.
So the reason you were saying all of the tributaries, the Potomac, the Severn, the South River, and they look like they're blue from back here, but it's because you're not getting any visualization.
Exactly.
That surprised me. I thought that wouldn't make any sense.
Yeah, well, you'll see why in a minute, because it's a limitation of satellites and why I'm now looking at drones.
I've been to the Canadian Rockies, and there are bodies of water that are turquoise.
Yeah, beautiful.
Yes.
So what's causing the turquoise? It's almost the exact same thing that's causing this gray water. It's just a different type of sediment, different type of mineral in it. First of all, there's very little algae in those glacial lakes, so there's really little green hue to it, but it's mostly like a clear water with a bit of sediment in it that's basically reflecting the lake.
Particles and colloids.
Yeah, exactly, yeah. All right, I just wanted to back up. So I've sort of said how we can measure all these things, but this is probably preaching to the choir. How many of you heard of the term eutrophication? Yeah, okay. Almost everybody, but for those who didn't put up their hand, I'll just briefly explain the term. And it's basically excessive nutrient pollution. So, you know, you fertilize your grass with like nitrogen and phosphorus to help it grow. And that same sort of concept is what defines eutrophication. It's an excessive amount of nutrients entering some sort of environment. And that's been a problem with Chesapeake Bay just through, you know, it's a problem globally, essentially, that, you know, as human population has increased so much and we have all this industry, that we really have excessive nutrients that are turning water. Basically, maybe it was like this 20 years ago. This is basically how I did this. I put a little bit of nutrients in here, and I put a ton of nutrients in there, and the phytoplankton, the plants, they loved it, so they started growing a ton. But fortunately, at least for Chesapeake Bay, some of the symptoms of eutrophication have been improving. Just going back to that Chesapeake Bay report card, it's a C now. I think it was a C minus a couple years ago. Any guesses why? I'm not 100% expert on this, and maybe the guy at Chesapeake Bay Foundation could clarify. Anybody have any ideas why water quality has improved? One of the main culprits?
Treatment plants are upgraded.
That's one, but that's not the major one, apparently.
Clean Air Act.
Clean Air Act. That's exactly right. Would you care to explain?
7 pounds of nitrogen per acre coming from Ohio.
Yeah. Yeah, that's exactly right. One of the biggest sources of nutrients to Chesapeake Bay was not, you normally think of sewage pipes or some really point source solution, thing, but in this case, a lot of it was just raining down from the atmosphere. And just through the Clean Air Act, a lot of the nitrogen that was hitting the bay, 10, 15 years ago is no longer. And that's, the algae loved the nitrogen, and now that there's a little bit less, the bay has responded, and it is a bit more clear now.
What was the source of nitrogen in the air?
Cars, coal is a big one. Yeah.
So is it because they're burning less coal, or is it because it's clean?
Because cars are cleaner.
I think both.
Yes. Coal's a bit cleaner, but not much.
Both, I think. Yeah. I don't know the data that well off the top of my head.
Certain coal, here's your prior science teacher, certain types of coal had more sulfur in it. And I had investment in a company, and they took accounting because they were buying coal from Michigan, and it had a lot of sulfur, and they couldn't burn it in their plants to generate electricity. So this high quality sulfur in the coal, they were not allowed to use it as a steam source.
So clean coal is a myth?
No, no comment. Okay, so I heard, I think it was from John, who was saying that you guys are now more interested in seagrasses. So one of the things with decreasing eutrophication, so on the right would be a highly eutrophic environment. So lots of algae, the water's super dark. And on the left is what we're trying to get to in our bay and in the estuaries and the rivers feeding the bay, is improved light conditions. So just by alleviating eutrophication, what happens is the algae can't take, there's just less biomass there, which makes the water more clear. And basically, because the water's more clear, that allows seagrasses living on the bottom of the water to start growing. And this is one of the applications for drones, is that we could fly over a sub-estuary. And it's pretty obvious from like a visual image, just a simple camera. But we can use a bit more sophisticated approaches with specialized cameras to actually try and detect and map submerged aquatic vegetation. This is a big thing they're doing out of Virginia. They're always doing these yearly maps of seagrasses throughout the bay, and they're just using basic digital cameras for that. So the whole technique is readily scalable to drones. But I'm working with a student now up at the Appalachian Lab, where we're looking at more sophisticated type of cameras to sort of speed up the process for identifying seagrasses.
Are you also capturing the depth that you're measuring?
So every time I fly a drone, I have a couple different ones. They all have GPSs on them. And just from knowing where we are, it's pretty easy to get the bathymetry. There's really good published data sets where people know exactly, especially if you know the tide too, that you're within a couple feet certainty of the depth that you're flying at.
So you're not updating other NOAA charts?
No, I'm not. I mean, if I wanted to, I could equip my drone with something called like a sophisticated radar. It's called LiDAR, where we could do bathymetry, but I don't have that much money.
Okay.
Okay, so we've talked a little bit about spectral characteristics and how these different colored bottles have different colors, and how we could sort of use that information to approximate things like concentrations of sediments, concentrations of dissolved organic matter, or phytoplankton or algae. So I just wanted to show you basically how humans perceive color and compare that to just a regular camera. So on the left, here we have once again that visible wave-like spectrum where we can see light basically across this rainbow from 400 to 700 nanometers. And these are basically how sensitive our eyes are, the rods and the cones in our eyes, to perceiving color. So yeah, it's kind of interesting. Like one of these things, like these light blue colors, we don't really, our rods and eyes can't really perceive, but at least that information is, processed in our brain for us to, recognize that that is in fact a different color, even though our rods and cones don't actually see it. But I think the point I wanted to make is that there's pretty big similarity between human vision and how a digital camera works. So that's basically, you've heard of RGB cameras. That's basically almost every commercially available camera, be it on your phone or in this case, it's a Nikon D1X. It basically registers how blue an image is, how green an image is, and how red an image is. This digital camera, though, they vary across different types of camera. I won't get into the nitty-gritty of it, but every time we, say, use a drone or something, we always want to look up that information, because if you took a picture and the spectral response or the spectral sensitivity of a camera changes, that's information you really need to know in order to accurately translate a picture into something of scientific use, of scientific value. Yep.
A question about the wavelength and what can you see, or what can the camera see? I'm an oyster farmer.
Yeah.
I'm interested in what's going on 20 feet below more than I am at surface level of water quality.
Yeah.
What can the camera do?
That's a good point, and I'm actually meant to bring that up. A camera is usually about, from what I've read in the literature, like about twice as sensitive as the human eye. But I mean, if you're interested in oysters 20 feet down below, and this is in Chesapeake Bay, so you never see those oysters. Yeah. But when they're at 20 feet, you can't see them. A camera's not going to help you out with that. That is a limitation of remote sensing and satellites, is that the color of the water is really only influenced by, basically how deep you could see. So if you were to wade into water, the point where your shoes disappear, that's basically the depth that we're able to monitor effectively.
The good news is most Middle East is really below is like 5 to 6 feet, it's not 20.
Okay, so you can see.
And that's with visible light.
That's also a very good point. That is with visible light. So yeah, something like radar or like even like Wi-Fi, like that stuff can penetrate to different deeper depths. I mean, that's like basically how sonar works. That's part of the electromagnetic spectrum. It can go deeper, but it's of limited utility for water quality data.
What about LiDAR? Because I was surprised to learn that every major municipality collects LiDAR data.
Really? Over water. So most LiDAR I think, uses red lasers. So that can't go very deep at all, just because water itself absorbs a lot of red light. But oceanographers are increasingly looking at like using a green laser, which can go down. Like if you're in the open ocean, you could probably hit 200 meters. If you're in Chesapeake Bay, it'll be past the vision that you could see, but not much deeper. Where was I? Oh yeah, so we looked at different, I compared how humans perceive color And compare that to a regular camera. I don't fully expect you to fully understand this slide. I'll just walk you through it slowly. Well, I'll go through it pretty quickly, in fact. These are just some of the satellites. You know, I mentioned that there's like 30 or 40 up there at least, whose sole purpose is to monitor the environment of the Earth. These are ones that I'll use on a day-to-day basis. Different names on the left. And they have different sort of trade-offs to using these. So one of these things, you probably can't see it, but it's resolution. And some of the best satellites, you know, we're looking at basically a kilometer resolution. So it can see a kilometer by a kilometer. If there's any spatial variability within that kilometer, it can't make sense of that. It just sort of amalgamates all that information within 1 kilometer data. So that I'm talking about the MODIS satellite specifically. And these colors that you see across are the types of light that they specifically monitor. So unlike, you know, here we have the human sensitivity, you know, very broad bands of blue, a broad band of green, and a broad band of red. Most satellites use very narrow range types of colors. So let's look at the very top one. This is Sentinel-3. This just went up this year. See a bit of violet, different shades of blue, shade of green, some brown, and a bunch of different ones in the red. So the point I want to make is that at least with these satellites, whereas we perceive essentially 3 colors, depending on the satellite, they could perceive you know, up to 10 or 15 different types of color. And this information is like pretty useful for us because it helps, you know, sort of differentiate between these things. Like I have pretty binary examples where this is all organic matter, this is all algae. But once you start mixing these things like you have in the environment, it can get pretty complicated pretty quickly. So the more sort of information we have on these different colors, that really helps us quantify, you know, exactly how much algae there are or how much dissolved organic matter there is. And the other thing is, one of the other things is just satellite passages. So a lot of these satellites, they pass over every 2 days, some of them every 2 weeks or so. And of course, you know, that requires there not to be any clouds for you to get accurate data. I should mention there is like this super fancy satellite that NASA's been planning for 3 or 4 years. It's called the PACE satellite. It's what's called a hyperspectral camera on it. And so instead of seeing red, green, or blue, it sees basically 256 shades of red or green or blue. And this is going to be a huge step forward in how we monitor our oceans and waterways with all that extra spectral information. But Donald Trump has specifically called it out to be scrapped. It's an $800 million satellite. They spent $4 million on it already building it, so hopefully it'll go through. Okay, so I've talked a lot about satellites. So why, and you know, we've got all this data. NASA makes it free. It's so easy. Why the heck would we use drones? So, and this was one of the questions that I was asked, and we're coming to the end of the talk. So here's basically, this is an image. This could be almost anywhere in Chesapeake Bay, but this is Harris Creek, which is sort of a sub-estuary of the Choptank River, sort of my backyard, a place that I do research. It's also home of an oyster restoration project. So people are putting in oysters. You know, the watermen aren't allowed to go in and harvest these oysters. And one of the big questions that we have is, will these oysters improve water quality? You know, oysters filter out algae, they live on algae, and they also filter sediment, which, you know, improves water quality, water clarity, habitat for fish. And, you know, just by improving water clarity, it also helps seagrasses. Except unfortunately, so this square box I have is, you know, 1 by 1 kilometer image. So a satellite that's measuring 1 by 1 kilometer you know, a lot of these sub-estuaries and little areas, satellites just don't have the spatial resolution to accurately image these things. I'm sure like the military probably does, but like commercially available stuff does not. So it's the technology is almost useless in these really smaller areas.
That's because that image is mixing together
Yeah.
the creek and
The creek and the
fields
land
on
and the
either
fields,
side.
yeah, and that's an optimistic, for reasons I won't get into, you know, satellites say, you know, 1 square kilometer, but in reality it's more like 4 square kilometers. So if you could take all that land and water together, you know, the image just becomes really noisy, and it's impossible to get reliable information off of there. So this is one of the great things about drones is, you know, even you can buy a drone for like $500 now with just a regular RGB camera. That camera alone, because it's doing that green and blue, we can probably get a decent estimation of chlorophyll. One of the drones I have, it has, you know, one of these hyperspectral cameras on it that measures all these wavelengths. So part of my research program now is, you know, I'll fly this drone and I'll go out into Harris Creek and just, you know, measure with a boat, go and take water samples, measure how much sediment is in the water, how much chlorophyll is in the water, make sure that what I think my drone, what my imagery is predicting, reconciles with what I'm measuring. Do that enough that I'm doing that enough now that I'm beginning to gain confidence in the technique. So now I don't even have to go out on a boat anymore. I could just fly the drone over Harris Creek. And it's an easy way to really rapidly monitor the bay or this region in specific, and in very high resolution. I mean, I could fly it at, so I'm bound by FAA regulations. I can't go above 400 feet, but that gives me, just the way my camera's designed, instead of a 1 kilometer spatial resolution, I'm getting somewhere around 4 or 5 centimeters. It's almost overkill, but it's still a great way to get water quality data.
Question?
Yep.
What does a hyperspectral camera for a drone cost now?
Great question. So you see these things, they've been marketed, and so I guess it's probably what's the 2nd generation, and now there's 3rd and 4th generation, because they're being marketed for like high precision agriculture. So a farmer could fly this out, and you know, these companies provide software and sort of the science behind this to say, okay, you should fertilize here, you should not fertilize there. So to answer your question, I spent $10,000 on this camera. So to be fair, every time I fly the drone, I'm sweating bullets. Yeah. And I should say, I didn't bring it just because it's too big and too heavy. I don't actually fly the drone anymore. It's all GPS controlled, very scientific. I say, okay, go here, hang a right, go here, go up the bay, turn around, come back.
What kind of drone are you?
Greg, tell the question.
Oh, okay, yeah, thanks. Sorry, the question was how much these cameras cost, and the most sophisticated is around $10K.
And what kind of drone are you flying?
What kind of drone am I flying? It's a commercially available, it's DJI octocopter, so it's got 8 blades. It's probably about this big. Probably about that big. 30 pounds with the battery pack. Most of the weight is a battery pack. I can get
How long will it stay?
20 minutes only, and because I'm an engineer, I'll fly it for 15. And then I'll swap out the battery and I'll fly it again. But they can go like 30 miles per hour without a wind, so you can get really a lot of data really quickly. So the whole package, drone, batteries, computer, is about $30,000. Sounds like a lot, but like, I mean, if presuming I don't crash this thing anytime soon, I'm gonna get a lot of data, and in the end, it'll be a not time saving, but cost saving way to measure water quality. Question?
My memory is that NOAA publishes with their satellite data, nitrogen data in addition to chlorophyll on the bay.
Yeah.
How do they get the nitrogen numbers?
So the question is how NOAA gets their data. So NOAA operates, I think maybe it's not NOAA, but people go out and measure these things directly.
Well, this was some satellites,
So I know all the satellite division people at NOAA. If they do it, it's extremely empirical. So it's guesstimate, I would think. I've never seen nitrogen data estimated from satellite data.
I would like to add to what this gentleman said. So Google Ocean adds detail to depths. So why couldn't we add your research to Google Earth to provide a really nice picture of depths and oxygen levels, moisture beds, whatever?
Yeah, there's nothing. It's just my time is the only thing that's preventing me from doing that right now. Google Earth has actually improved a lot. There's something called Google Earth Pro, and now you can get add-ins for real-time satellite data. And this was actually the app that I was hoping to show you guys, where we had our open house at Horn Point Lab, and I was showing people real-time imagery almost real-time imagery, like 6 hours ago, of the California wildfires, and then switching over to a different satellite data and looking at like the carbon monoxide plume blowing off into the Pacific Ocean from those wildfire data. So it's just a lot of satellite data is already available online, and it's increasingly easy to access. But I know, if I'm measuring drone data, I don't know who at Google I should speak to for publishing this. But I should add this, for every research grant a scientist ever gets these days, we have to have a specific data plan where anything we collect is made publicly available.
So could you explain again, you touched on, how did you correlate your photographic data with what's actually going on in the water?
Yeah, so I was kind of breezed over that. Yeah, sorry about that. So do you remember that pure water itself is blue and algae are green? So the very most basic explanation is the more green the water is, the more algae there are. That's the easiest explanation, but I should say there's probably about
You actually tested that. I mean, you actually took the water samples.
Yeah, sorry, I took the water sample. That's basically my entire research program for the last year and a half has been going out, making these measurements and building, the requisite paired data to give myself some confidence that this type of algorithms are going to work.
It's not a devil's advocate because I firmly believe in what you're doing. But I talked to Don Merritt, who runs Oyster Hatchery at Orange Point a couple of years ago, and I'm very much a data person, so I wanted to collect DO and all that. He said, well, David, why don't you just go and use, I think it's NOAA, has a voice system. Why don't you just use that for the data?
So yeah, NOAA, the question is about getting data on Chesapeake Bay. So NOAA operates buoys, and they measure dissolved oxygen, they measure temperature. Some of them measure, not exactly algae, but say a proxy of algae. But they're at very limited locations and only in the main stem of Chesapeake Bay. So if you're interested in water quality in a lot of the tributaries, be it Severn River or my river, Choptank River.
West River.
Yeah, I got to go out and do it myself.
Okay, because the other follow-up is, what particular parameters in water quality lend themselves to drones particularly?
So the question was, what water quality parameters lend themselves to drone? Basically, the three things that I have up here, that anything that interacts with color. So oxygen has no influence on water color. Temperature does, but I just don't have that instrumentation. So basically chlorophyll and sediment loads. And you know what? That's in and of themselves, those are very useful data because, just the way eutrophication works, it's super important to know that stuff.
Is anyone doing the same drone technology for the Severn River?
Not that I'm aware. The question is, anyone doing the same? You have your hand up, do you know? Yeah.
Yes, thank you, Professor Silsby. The Severn River Association and the Baton Creek Conservancy are presently operating a drone. DJI Phantom 3 Pro. And I think I'd like to really challenge you to get one more grant application for citizen science of collaboration between the Severn River Association and the Horn Point Lab to evolve our drone capability to work with you to really try to demonstrate what these opportunities are, particularly with a hyperspectral camera.
Yeah. So thanks very much, Dave. Dave emailed me a couple days. I know we talked over the phone a couple days ago. And I already have in mind exactly. I'm going to ask Marilyn Seagrant for maybe like $10,000 and see if we can get some sort of thing going. Don't applaud yet. I have 15% chance, folks, but there's no harm in trying. Exactly. Yeah. And I was hoping it would be publicly available now, but I have some friends in Europe that are scientists that are just making an app where you can just take a picture with your phone. The app controls the camera a bit on your phone, and it sort of records the information, what type of camera you have, and from that information it says, okay, it looks like this amount of algae, this amount of sediment in the water. That should be out in the next couple months. And that type of application in science could be readily applied to any drone footage that you have. All right, I had a couple more slides, but I mean, the other thing is, because I harped on satellites a lot, and 60% of my work is using satellite data. This is a picture of the Bay Bridge road, lots of clouds. Satellites, the other limitation is just basically clouds. They can't see through clouds, and that happens a lot. So it's another advantage of using these drones.
When there's cloud coverage, you have to correct?
When there's cloud coverage, there's nothing, out of luck.
With a drone?
Oh, with a drone you're fine. I was presuming you're under the clouds.
Green is green.
Green is green, yeah.
Clouds or something.
Yeah, and I don't want to get too heavy into it, but one of the huge challenges of using satellite data is things like haze or water vapor. The light leaving Chesapeake Bay. Like these satellites are 7,000 kilometers. That's me being Canadian, using my metric there. 4,000 miles up in orbit. So a lot of things happen to that light between it bouncing off Chesapeake Bay and reaching a satellite. And it's a huge, complicated field and something that you don't have to worry about when you fly a drone. It's one of the principal advantages.
But what about the light absorption going through the water in sunny day versus the cloudy day?
Yeah. You know what? That's a great question. Because this was my last slide, and I just meant it as a jumping off point to discuss. But you guys are asking really awesome questions. So I just wrote this. I was in meetings and teaching all day, so I just had a couple of minutes to quickly think about this as I was running out the door. And the bottom point speaks to what you were saying, is the importance of metadata. Does anyone know what metadata is? Yeah, metadata is like, if I make an observation, or I say, in this case, I fly a drone, write down, where you were, what time of day it was, whether it was cloudy or whether it was sunny, and that type of information really helps. There's a very more specific answer to your question, but it gets a bit complicated. So normally when I fly a drone, I'll lift it off from like something that's perfectly white, and just based on the camera looking at that level of white, I could use that sort of standardize all my subsequent measurements, and that's sort of a standard thing we do in the field. Yeah. All right. I'll take any more questions. Yeah, I'm here all night. I had an accident with a drone. I have a 13-year-old whiz kid working for me, and he's doing stuff on computers I don't even understand. But he did crash the drone once. It yeah, like $600 in repair, so it was not the end of the world. Yeah.
Are there red algae blooms?
That's this is another good question. Yes, there are red algae blooms. The example I gave was green algae just to make things straightforward. But they're, especially in the upper waters of something called dinoflagellates, cause these red algal blooms. They're pretty common. And that's just one of the extra challenges that we have with drones is, when we see this color of red, how much of it is tannin, how much of it is something else. I didn't want to get into the science, and because this really gets really heavy into the math. But one of the advantages with a hyperspectral camera is you can look at very specific features in this sort of color spectrum, where then you can be able to differentiate a red algae from basically anything else.
Have you had any reaction to any of the landowners or residents viewing your drone?
Well, that's the great thing about using drones to study rivers and bays, because I'm allowed to be out there. I'm not infringing on anyone's property rights. But just through Horn Point, we have a lot of good connections in our watershed. So often I'll go up and fly it off of a dock of someone who's friends with the lab. Yeah, and people are very happy to let me do that.
So your drone is always within line of sight of you, or it's gone?
No, FAA regulations require it to be in line of sight of me. Yeah, for now.
You need a really fast skiff.
I do. We have a really fast skiff.
There you go. Sounds like fun.
I've landed it on the fast skiff, and it's a bit hair raising.
Do you have a recorder on the drone, or does it come back to you? How do you get the information?
So because it has a GPS, basically, in fact, it's this computer I use. I hook it up to the drone beforehand, and I tell it to fly, 2 miles this direction, half mile here, come back, and then it just returns. And then it's all programmed, really. You don't actually fly these things. The remote control, like I grew up at a time, and you guys are older than me, but sorry, but you remember maybe video games back in the day, there's 1 or 2 buttons, and then I haven't played video games in forever, but the controllers are there's 700 buttons and all these toggles on it. The drone is even worse. There's 800 buttons, and every button does something important. So I forego that, and I use a computer to tell it exactly what to do.
His question is, how do you record
On the drone or being back?
Oh, sorry. I apologize. I didn't understand. So yeah, basically I have a camera and a mini computer like a Raspberry Pi. I don't know if you've heard of that. These little microcomputers. I record onto the computer. When it comes back, I download the data onto my computer. It's just way too much information for it to be beamed back to anything else.
Is there any useful data in the infrared, any useful water quality data in the infrared spectrum?
In the infrared spectrum, it depends how far you go out. If you go far enough in the infrared spectrum, you can get water temperature. There's lots of good infrared applications for terrestrial data, but not that much for aquatics.
Did I miss you talking about SAV?
I did talk about SAV. Love SAV.
How much do you use ArcGIS?
Question was how much I use ArcGIS. I don't use ArcGIS. I use open source software that basically I more or less write it myself. I don't like paying commercial software fees.
Do you have an assessment of the water quality in Harris Creek as a result of oyster restoration?
Too soon to tell. I've got about a year of data, and as the oyster restoration progresses, I hope to answer that question better. But I'm pretty confident by planting oysters it's going to improve water quality. That's sort of a paradigm almost.
How wide of an area do you capture with the camera?
So I normally fly my drone at 400 feet. So within that, I think, let me remember the math. I think it's something like 600 feet width, and then within that 600 feet, I could parse that out into a lot of little separate channels, just how the camera works.
What drone model do you use and what camera?
Sorry, what drone?
What model or brand of drone do you use?
The brand is called DJI. It's out of China, and it's the S1000 Plus. And the camera is from this company in Texas called Bayspec. Bayspec.
So how can you turn this in, your research, into something that's money-making?
Oh my God, I get that question so
So,
often.
okay, so I like to fish.
Yeah.
Right? How can you improve my fishing report on a daily basis? Okay, so you're like measuring, algae plumes and stuff like that.
Yeah.
Oxygen, where the fish like to live. If you could present that someplace, maybe some commercial concerns would buy it and help pay for your cameras.
Yeah, I appreciate the question. I'm not an expert. We have people at our institute that are slowly trying to push me in that direction of sort of monetizing this type of application. But it's honestly, I'm interested in. If I wanted to make money, I wouldn't be a scientist. Yeah.
Just saying.
No, I appreciate the question. There are some applications, but it's mostly environmental monitoring. Maybe I'm not imaginative enough.
Changing the subject slightly, how do you keep that slim figure?
Family genetics and ultimate frisbee. All right, thanks very much, everybody. I really appreciate coming out. And I encourage you, you guys are like super informed audience. I encourage you to like trawl through the UMC's webpage and look at the directory of all faculty. And if you see something, we're really interested in seagrasses or something else, we've got experts in everything. Talk to them, tell them about how I came here. I mean, it's such a great time that, I think probably get a lot more of us down here.
Okay, good. Okay, Greg, thank you very much for coming. Yeah. I just wanted to let everyone know that we're talking about fishing. Well, the subject for our next meeting here is fishing and the Severn. So if you're a fisherman, hopefully you'll come to our next meeting here.
I'm always looking for ideas.
Okay. Thank you for coming.